In today's video, we will look at a new method for evaluating a limit that has indeterminate form, and that method is known as L'Hopital's rule. We will see that this method only applies to two specific indeterminate forms, but with proper manipulation, we can fit just about any limit into one of those two forms. The rule itself suppose that f and g are differentiable functions over an open interval that contains a, right? And these functions don't necessarily have to be differentiable at a itself. Now, if the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is also equal to 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Assuming, of course, the limit on the right exists or is infinite, either plus or minus infinity. Now, these also hold if we are considering one-sided limits or even limits at infinity. We will now go ahead and prove this. For this proof, we shall only consider the special case when f, g, f prime, and g prime are all continuous over an open interval containing the point A. So since the limit as x approaches a of f of x is equal to 0, which is also the limit as x approaches a of g of x, and f and g are continuous at a, it follows that f of a would have to equal 0, and so does g of a. Therefore, what we can do is we can write the limit as x approaches a of f of x over g of x as the limit as x approaches a of f of x minus f of a over g of x minus g of a. We can now write this as the limit as x approaches a f of x minus f of a over x minus a, and then over g of x minus g of a over x minus a. Now we can use the quotient rule for limits, which says this is the limit as x approaches a of f of x minus f of a over x minus a divided by the limit as x approaches a of g of x minus g of a over x minus a. However, that is precisely f prime of a over g prime of a. But both f prime and g prime are continuous at a. So we can write that as the limit as x approaches a of f prime of x over the limit as x approaches a of g prime of x. And then using the quotient rule for limits, once again, that is the limit as x approaches a f prime of x over g prime of x. This was our desired result, and so the proof is complete. Now, it is offered without proof that L'Hopital's rule also applies if the limit has an indeterminate form of infinity over infinity, right? So this limit here, as stated, this is 0 over 0. Right, but this rule would also be valid for infinity over infinity. And again, that statement is offered without proof. We will now look at several examples. Limit as x approaches 1, sine of pi x over the natural log of x. If we were to plug in 1, we get sine of pi over log of 1, which is 0 over 0. So this is the limit as x approaches 1. Now, using L'Hopital's rule, we take the derivative of the numerator, pi cosine of pi x, over the derivative of the denominator, 1 over x. This becomes the limit as x approaches 1 of pi x cosine of pi x. Now if we plug in 1, we get pi times cosine of pi. Cosine of pi is negative 1, so our limit here is negative pi. Let's now look at the limit as x approaches infinity. E to the 1 over x minus 1 all over 1 over x. If we were to plug in infinity, we'd have e to the 0 minus 1. Well, that's 0. And then we'd have 1 over infinity, that's 0. This is indeterminate form of 0 over 0. So, L'Hopital's rule says take the derivative of the numerator, which is negative 1 over x squared e to the 1 over x, over, now the derivative of the denominator is negative 1 over x squared. This will become the limit as x approaches infinity of just e to the 1 over x, which is e to the 0, which is 1. So this limit is 1. Now let's consider the limit as x approaches 0, sine of x minus x all over x squared. If we plug in 0 here, we're going to get 0 over 0, so L'Hopital's rule. Derivative of the numerator, cosine of x minus 1 all over the derivative of the denominator, which is 2x. Now at this point, we can factor out a 1/2. Leaves us with the limit as x approaches 0, cosine of x minus 1 all over x. That is a special limit that was derived earlier. That limit is 0, so our limit is 0. Let's take a look at the limit as x approaches infinity of 3x plus 5 over 2x plus 1. Plugging infinity gives infinity over infinity, so we use L'Hopital's rule. So let's take the derivative of the numerator over derivative of the denominator. That just becomes 3/2. Next up, we have the limit as x approaches 0 from the right, log of x over cotangent of x. This will give us infinity over infinity. L'Hopital's rule. Limit as x approaches 0 from the right. Derivative of the numerator is 1 over x over derivative of the denominator, which is negative cosecant squared of x. This will be the limit as x approaches 0 from the right of negative sine squared x over x there we have two ways to proceed here. Let's just do L'Hopital's rule again. Pull out that negative. Limit as x approaches 0 from the right of 2 sine of x cosine of x all over 1. And this limit is equal to 0. Alternatively, what we could have done is from here, we could have written this as the limit as x approaches 0 from the right. Again, put a negative out in front. Right sine squared is sine times sine. Then we have sine x over x times sine of x. That would have been negative limit as x approaches 0 from the right, sine of x over x times the limit as x approaches 0 from the right, sine of x. We know this first limit goes to 1. This second limit would have gone to 0, and so we still would have gotten 0 as our limit. Okay. Next, let's look at the limit as x approaches 0 from the right of x times the natural log of x. Now, if we plug in 0 from the right, we get 0 times negative infinity. This does not fit one of the two forms required for L'Hopital. However, we can force it into one of those two forms by writing the limit as x approaches 0 from the right of natural log of x over 1 over x. Now we get an infinity over infinity form. So now L'Hopital's rule would apply. 1 over x over negative 1 over x squared. This simplifies to the limit as x approaches 0 from the right of negative x squared over x, which is negative limit as x approaches 0 from the right of just x. And that limit is, of course, 0. Now we have the limit as x approaches 0 from the right again. This time, 1 over x squared minus 1 over tangent of x. If we plug in 0, we will get infinity minus infinity. And again, that does not fit one of the forms, but again, we can force it into one of those forms. So limit as x approaches 0 from the right, 1 over x squared, right tangent, 1 over tangent as cotangent, which is cosine over sine. Now write this as a single fraction. Sine of x minus x squared cosine of x all over x squared sine of x. This now fits the form, so L'Hopital. Cosine of x minus become plus x squared sine of x minus 2x cosine of x all over x squared cosine of x plus 2x sine of x. Now if we plug in 0 from the right, this becomes 1. This is 0. This is 0. So we have 1 in the numerator, 0 in the denominator. We're approaching from the right. That means all the values are going to be slightly larger than 0. Cosine's positive, sine is positive, x is positive. The entire denominator will be positive. That makes this positive infinity. All right. Let's now look at limit as x approaches infinity, x to the 1 over x. Now, here, we're going to get infinity to the 0. Well, that's definitely not proper form. But what we can do is write this as the limit as x approaches infinity, e to the log x of 1 over x, or x to the 1 over x. That is the limit as x approaches infinity of e to the log of x over x. Now using the composition rule and continuity, this becomes e to the limit log of x over x. So now really what we're doing is we're focusing on this limit right here. This is infinity over infinity, so we use L'Hopital. 1 over x over 1. That limit is 0. So our limit, which was the limit as x approaches infinity of x to the 1 over x, wound up being e to the 0, which is 1. And finally, let's take a look. Limit as x approaches infinity of x to the sine of x. Right? Now again, this is going to give us an undefined limit altogether, first of all. All right, but let's take a look at doing this. So again, e to the natural log of x to the sine of x, which is the limit as x approaches infinity of e to the sine of x times the log of x. And that is e to the limit sine of x times log of x. All right, so again, now our focus will be on this limit. This limit is still undefined. But we can write it like this. Log of x over the cosecant of x. Now what we find is we have proper form. Using L'Hopital, 1 over x over negative cosecant cotangent that'll equal the limit as x approaches infinity of don't forget your negative sine squared all over x times cosine of x. This is still indeterminate. Negative limit as x approaches infinity, 2 sine of x cosine of x all over negative x sine plus cosine. That's why none of this made sense to me. These are not infinities. These should all be zeros from the right. Thankfully, that is an easy enough fix. My apologies. Now if we plug in, okay, you can see now this is making a lot more sense to me. Plug in 0 from the right here. That is 0. Once again, our limit here will equal e to the 0, and that limit is 1. And that concludes this video on L'Hopital's rule. The next video in this series will begin to analyze how we can sketch graphs of functions simply by using derivatives. We begin that process by studying extrema. I will see you all in that video.